Hey, welcome. We're almost at the end of this little jaunt through differentiation. Well, at least introducing the concepts and the overriding principles that are needed to know. Those of you who are watching Internet Land, hi, welcome. Don't worry about this first thing here that by the end of teaching, I'm not asking you to submit work. This is actually for the guys I'm currently lucky enough to teach. So you can ignore that completely. Let's go straight into this because it's a relatively short video. Limit notation. Now we've already, as I say, briefly touched on this when we had the ideas of differentiation from first principles. Wow, that seems like a long time ago, doesn't it? But you looked at the idea of when you had a curve and you had a point here and a point here, and you said, well, let that be x and comma f of x, and let this point here be x plus h. And that was a silly use of brackets. So we had, let that point there be x plus h, and then that would be f of x plus h. And you used the general ideas. I said, well, if we were trying to find the gradient of the point that, the gradient of the line that joined those two together, then we knew that the gradient would be equal to, well, y2 minus y1, so f of x plus h minus f of x, all over what effectively turned out to be h. And then we had to make sure that we had this limit as h tends to 0. Now the reason we said as h tends to 0 is what we're trying to do is we're just using a wonderful little math trick to say, well, if we imagine that that point gets closer and closer and closer, and this value of h here gets smaller and smaller and smaller, then we should be able to find out what the value of the gradient at that one point would be. That was the idea. And limits are really useful. Okay, they're used a lot in university. We sort of touch on them here, and I think they're used more in spec. But if we look at this question here, then all this is saying is we are trying to find the limit as h tends to 0. So as h gets smaller and smaller and smaller, what would the value get closer and closer to? What would the value of my function get closer and closer to here? Well, if we look at it as it gets smaller and smaller and smaller, that whole term there would effectively become 0. And so we would be able to say that as h got 0, closer and closer and closer, then our function there, our function of x, our value would get closer and closer to the value of 3. Now this, in this situation, is nothing to do with differentiation. It's actually just saying, as we move, and this graph is in terms of h, as h gets closer and closer to the value of 0 on the graph, what will my function become? And it's 3 in this situation. Okay, why? Well, ultimately, this is going to be some form of quadratic. It's going to go through a turning point of 0, 3. And what we're saying is, if this now is h, and this is f of h, then as we get closer and closer and closer to 0 from both sides, we notice that the value of the function there gets closer and closer to the value of 3. So as x gets closer and closer to 0, the y value gets closer and closer to 3. Same thing here. This one's in terms of x, something we're more. So it says, well, excuse me, considering this function here, 3x squared, as the x value gets closer and closer to 2 from both sides, what will my function value? And here is my little graph just to show you, right? So it's a really randomly badly drawn graph, but graph of 3x squared. If we have our x value there as 2, we know just using some basic algebra, therefore that 2 squared times by 3 is 12. So we know that this point here goes through 2, 12. And you could argue that I've already worked all this hard thing out for me, but we're saying as x gets closer and closer from both sides to the value of 2, what does my y value get closer and closer to? Well, in this situation, you'd write there 12. So limits, just reading limits is really important. And then we get onto these wonderful problems. Now, generally speaking, most of the questions that are in the Cambridge Essentials textbook are relatively straightforward, and then they throw in some doozies. So let's consider this graph here. The function of x is given by 2x squared minus 5x plus 2 all over x minus 2. First things first, we can see automatically that in this graph, if I put the value of 2 in, what's going to happen on the bottom? Well, if I put the value of 2 in there, I'm going to get 2 minus 2, which gives 0, and anything divided by 0 is undefined. So we already can see now in this situation that we don't know automatically what the value of the function is going to be at 2. Now I could draw it. I could absolutely draw this function. And having used my Desmos and my CAS calculator or whatever way I've done it, I actually find out that my function, this function here, becomes a straight line. that isn't defined at the point equals 2. Now, we already know it's not defined at the point over 2. We've already proved that here on the bottom. So if I draw this, I've actually got to put a open circle at the point 2, 3. We're going to say, where did I get the 3 from? Well, if you put the function, if you put 2 into here, you actually get 3 out. So by drawing the graph, if we were to say, looking at my values as x gets closer and closer and x gets closer and closer, then I know that it's actually going to get closer and closer to the value of 3. So if I was to write the limit of as x gets closer to 2, f of x is equal to, we could actually say, as x gets closer and closer and closer, the limit would suggest that the value is getting closer and closer and closer to 3. I know it's not defined at that point, but we could say that the function is getting closer and closer to that value, which is really important. How on earth can we do this algebraically? Well, first things first, my advice to you is this. Whenever they give you a quadratic on the top and a linear factor on the bottom, or a linear function on the bottom, it's a trick. It's a huge trick. Factorize out the quadratic. And so I know I've already done the working here, but I'll just do it again. You've got 2x squared minus 5x plus 2. I love using my T method to do this. First term times the last term is 4. Find the factors of 4, 1 and 4, 2 and 2, 4 and 1. And then try and work out which of these add to give my middle term. Well, I want them to add to give negative 5, so in which case they all have to be negative, because a negative times negative will give me that positive. So I'm looking at minus 1 and minus 4. So 2x squared minus x minus 4x plus 2. I've now got 4 terms, so I can do factor pairs. That becomes x, 2x minus 1. Take out, what's that, minus 2, gives me 2x minus 1, which gives me x minus 2 and 2x minus 1. So when I factorize that top, I get 2x minus 1 and x minus 2. OMG, hold on a moment. That x minus 2 is freaking awesome, because it now looks like it's going to be able to cancel with the bottom of my fraction. Thank you very much, I is a happy bunny. And that's exactly what I've done here. So what I've done is I've re-expressed the function by writing the top as a product of 2 linear functions and the bottom as x minus 2. I've cancelled them out, which tells me that my function, and we were expecting a straight line. We were expecting a straight line of 2x minus 1. Oh good, it crosses through at minus 1. And so now I can actually use my reduced algebra to say, well, I can now consider as the limit as x tends to 2 of my function of x is exactly the same now as the limit as x tends to 2 of 2x minus 1. And remember, that looks dreadful, just get rid of that bracket and try that one again. All we now need to do is put the value of 2 into this equation. And what happens? 2 times 2 is 4, minus 1 is 3. And lo and behold, we are told that the value comes out as 3. Now, again, algebraically, drawing the graph, using your CAS calculator, lots of different ways of doing this. But I just need you to be aware that this is how we use limit notation. There is a lot of limit algebra here. And so, for example, I'm just making this screen a little bit smaller to give you some examples. There are a number of things that we can use to try and make limit algebra and calculations much, much easier. These are great to put in your summary notebooks and just use them if you need to be. I'm not going to go through too much of them here. They're sort of just there to try and help you. But what it's saying is where you have the limit of 2 functions added together, you can actually split them up as the limit of the first function plus the limit of the second function, making sure that you have x tends to a, which is just this value you're trying to go to. They're suggesting that if you have the limit of k times a function, that constant can be moved outside to become k times the limit of the function. That seems fairly self-explanatory. And limit of when you have 2 functions multiplied together, they can be split up into the limit of the first function times the limit of the second function, and likewise the same with division. Much of this makes perfect sense. One of the most important aspects of this course, I think, is the idea of continuity. We have looked a little bit in a previous video about differentiability at a point, and we must look at things from both the left-hand side and the right-hand side. You're looking at considering as a graph moves to a particular point. So for a function to be continuous at a point, we need to consider those values of f of x as they approach the point we're looking from both the left and the right. So if we look at this particular function here, automatically I can look at it and go, well, it's discontinuous. There's a discontinuity. How do I know that? Well, firstly, here is my line. So there is my line. There is my obvious original function. It's got an open circle. And where it has an open circle in the line, hello, it's discontinuous. There is no value at that particular point. It's a break in the graph. So I can even just look at these things and go, it's discontinuous. What's this floating point all about? Well, basically, it's just saying, well, at that value, when I put x equals 1 into this particular equation, I don't get the value of 6, which is what I'm expecting. I actually get the value of 12. So what I'm suggesting is we now need to show an examiner, or we need to be able to use mathematical language to describe this discontinuity. Now, the first thing we do is we actually say, when f of 1, when we put 1 into my function, we get 12. So I'm stating what happens at that point of discontinuity. I know there's a discontinuity. I'm stating that when I put 1 into my function, I actually get 12 out. Well, then we've got to say to the examiner, but I need you to realize that when I approach either side from both the left and the right-hand side of x equals 1, I'm actually going to get a different value than what I get. And the way we do this is we use this great notation of lim, let's just rub that out, try again. We use this great notation of lim x tends to 1 negative or x tends to 1 positive, right? Now, what that actually means, this little floaty positive and negative, just means that we're coming at it from the negative side and the positive side. So coming at it from the negative side means we're coming at it this way, and coming at it from the positive side means we're coming at it that way. So it's just a very clever way. And again, what we now say is, and we have to formalize this, that the limit as x tends to 1 from the negative side, we have f of x is equal to 6. And likewise, as the limit of x tends to 1 from the positive side, we get f of x is equal to 6. And because the values from the left to the right are not the same, then we say, therefore, there is a discontinuity at x equals 1. This really important, all right? Really, really important. I mean, in many cases, the questions may just say to you, where's the discontinuity? But if they ask you to prove it, you have to say the point, the actual value you get at the point, and the values you're expecting or getting from either side. All right, that's the end of this lesson. Thanks very much for listening. Wow. I look forward to seeing you in the next one. It's been so great having you watch this video that I'd like to see you again and again and again. Wow, we could make some amazing maths together. So, if you'd like to, and you'd like to be updated as to when I upload new videos, why not subscribe by clicking the button on the right? Otherwise, if you want to click and see another video created for this type of series, then click the video on the left. All right, well, you have an awesome day, and I look forward to seeing you again.